Welcome to the live Learn More About stream, where we're about to get the lowdown on the role that weather plays in VHF propagation from one of the leading experts in the field, Jim Bacon, G3YLA. Now you can post questions to all the speakers using the YouTube chat facility. We'll do our best to fit them in, and don't forget to include your name and call sign. And do keep your feedback coming in. Comments very welcome at rsgb.org/feedback. So next, learn more about VHF propagation and the weather. Those of us of a certain age will remember Jim Bacon, G3YLA, as a BBC weather forecaster, often to be seen on television wielding his magnetic cloud and raindrop symbols, and some of them even used to stay in place, didn't they, Jim? Anyway, technology has moved on, so without a magnet in sight, it's over to you, Jim.
Thank you very much, Jim. Well, it's really nice to be here, and I have to say some fantastic presentations so far this morning, and really enjoyed both of them. The only thing I'm missing so far is the breakfast from the convention, but I'm sure we can fix that at some stage. Right, well, this is going to be originally a talk about the preparation of the GB2RS propagation section in the news that comes out every week. And I was going to describe some of the things I go through in preparing that. And there's quite a lot of work goes into it. I usually carry out the task on a Wednesday evening after I've been to my local Norfolk Amateur Radio Club. I do it when I get home. And that then is a forecast for the whole of the following week. So it's equivalent of a 10-day forecast. So quite a lengthy spell ahead in time in terms of weather models and what they're telling us. So takes a bit of thought, and actually I think overall it's quite a challenge, but it's been a really interesting one, and it's then led on to quite a few developments in other areas that I'm interested in, particularly propagation and how it's linked to weather. Now there's not going to be time to detail all of the individual components of this, so I'm going to major on a few of them. Now there are of course the standard ones, for example tropo, which is basically driven by areas of high pressure and temperature inversions and changes in the refractive index of the air. And then we have Sporadic E, which is my current area of interest, and really a lot of work going on there, both in the professional research field and in the amateur world, and tremendous advances being made each year in terms of our background knowledge and how we interact with it. Then we have rain scatter, which I'm not personally involved in, and it's something for the gigahertz boys and girls, but it is a very interesting mode and very strongly, obviously, affected by weather. And lastly, I just want to finish up with a few words about PropQuest, a website which I and a colleague at work developed to help put some of this material out there so amateurs can keep in touch with it more easily. Now, there's not going to be time to do all of this in detail, as I said, so I'm going to focus on two of these, Sporadic E and PropQuest later on. But just along the way, we'll mention these other two items as well. So let's get started with Tropo. Now, we're all used to Tropo. We've had some periodically quite recently. Autumn is a typical time for it. And Tropo is, as we know, it's a phrase that gets a contortion from tropospheric propagation or anomalous propagation, anaprop. Amateurs you'll hear describe, well, a bit of a lift on today. And all of it can be followed by following weather charts. And that's one of these revelations in amateur radio that you have a shack and you either end up talking about the weather on the air to fellow amateurs, or you end up having your operations, your propagation affected by weather. So it's a good fit for this subject. That little scatter plot on the left there is a picture of what a rainfall radar would look like if you didn't filter out anomalous propagation effects where the radar beam is ducted into the ground and you get echoes coming back that don't move. Well, they're not formed by rain, which is moving with the clouds. They're actually formed by the ground. So a lot of the modern systems, well, they all manage to eradicate that quite successfully. So when you see a television weather map or a forecast with rain radar, you hopefully won't see any of those spiky feathers going out of anaprop and surface ground effects. The thing to have in the back of your mind with this business about tropo, though, and it's a key thing really, is that it's all how the refractive index of the air changes. And the changes are due to the weather, but this is where weather comes into it. The refractive index of the air is a function basically of moisture, temperature, well, and pressure, but over the depth in the atmosphere that we're looking at, the pressure doesn't change much. It serves as just a marker of where we are, how high above the ground we are. The things that do change a lot are moisture and temperature. And in particular, moisture is the one that we probably should focus on more than temperature, although you wouldn't get tropo without a big temperature contrast as well. Anyway, to explain what that means, let's just have a quick look at this graphic. On the right-hand side, you'll see a typical schematic of a weather map with a big high. Now, this is a tropo operator's sort of holy grail. This is what you want. You want a nice big high. And the idea is that in an area of high pressure, air is sinking on a grand scale. It's not just in one place. When we have shower clouds, for example, and thunderstorms, rain's going up very locally, you know, the width of about 1 kilometre across or whatever, just an upcurrent within the cloud. Areas of high pressure, the air is sinking over thousands of square kilometres, and it's a very gradual, slow descent. And that slow descent causes a temperature inversion to form. And on the left-hand image, you can see, probably if I can move the, here we go, I can move your the cursor here. You can see instead of the temperature decreasing as you go upwards, I won't explain the background to these charts other than these are things that we use in the meteorological world, and they're special graphs for plotting how temperature and moisture vary as you go up in the atmosphere. Just take it from me that the normal procedure for dry air is for the temperature to fall at this sort of rate. And if it starts to level off or even increase, then that's what we call a temperature inversion. You've inverted the fall of temperature into either a steadying off or an increase. And this top one here can be caused by this subsiding air in the middle of a high pressure system. Weather fronts will do it as well, actually. So that's worth bearing in mind if you want that extra point during VHF NFD. The other common way of finding a temperature inversion is to wait till you have a clear night, like we did over here in Norfolk and Eastern England last night. Clear skies, all the heat radiates away into space from the ground. And the temperature trace at the bottom of this map, the temperature falls at the surface, but it doesn't fall quite so much just above the ground. Because, as you know, air is a good insulator. You have air gaps in brick walls, and you have you know, boundaries where heat doesn't transmit very effectively through it by conduction, by touching it. So air is, relatively speaking, a good insulator. And what that means is the temperature at the surface here can drop to a lower, much reduced from the air temperature just a little bit above the ground. So instead of starting at the surface and having the temperature decreasing as you go up, you find it increases. So it moves to the right on the graph. And that's a temperature inversion at the surface. And it's caused entirely by the cooling of the ground overnight. And in fact, what it kind of implies, doesn't it, that as the nighttime finishes and the day comes along and the sun comes up and warms the ground again, then this blue line here at the end will gradually edge across to the right, and the temperature inversion will be dropped. So if that surface inversion is causing you some tropo and giving you some enhanced points in a VHF NFD, then don't expect it to last after you've had your breakfast. Work the tropo until it fades, and then get the frying pan on. I don't know why I'm fixating about breakfast at the moment, but anyway, there we go. So this is kind of a visualization of it, isn't it? This picture on the left, fantastic picture from a GW friend, Ian Collins, who took this many years ago from a hillside in Wales. And you can see how the mist and low cloud and fog in the valley has got a very solid sort of looking top to it. And that's a classic signature of an inversion. And the schematic on the right shows how as air near the ground, even on the top of a hill, cools, cooler air is more dense and it flows down the side of the mountain, and you get this puddling in the bottom of a valley, where also because of moisture down there, cooler air, you'll find you tend to get fog forming and so on. But above that, you could also find there's a subsidence inversion caused by an area of high pressure. We might get a hint of that here in the cloud in the distance on the left-hand picture. So you can get multiple inversions. In fact, there are huge number of inversions, almost unlimited number on some days. When you look at the clouds and you see multiple layers of clouds, that means there are lots of inversions. The idea is that you want to trap your signal underneath an inversion to get the maximum distance. The only problem is, of course, you find a hill there and you're not going to go through that hill. But nonetheless, that's the aim. So the normal VHF rules is go to the top of a high hill and work your DX from up here. When there's a surface cooling inversion in the valley and your tropo's down here, there's no point getting out of your shack and clambering to the top of the mountain, at least not to begin with. Okay, this is a wonderful graphic which I use periodically from Marcus Walden, G0IJZ, who looked at an elevated duct which was due to a subsidence inversion because of high pressure from a GM station to an F station on the northern slopes of the Pyrenees. And the red area on the left is where the signal is strongest. And then it gets trapped underneath this inversion, and you can see the line of the inversion. And although there are losses as you move away from the signal source, it manages to survive very well, going across Wales, going across the hills and moors of southwest England, the high ground in Brittany, and all the way down across western France till it meets the foothills of the Pyrenees. So inversions and the ducts that they form, really important parts of working VHF DX, and they're all produced by high pressure. Now, computer models are very good at forecasting these. There are two good sources available on the web. F5LEN, Pascal, produces a very good site, as does William Hepburn. And these were two graphics I took back in the spring of the same time, same date. So just to think about this for a moment is to say, well, they've got strong similarities. You've got areas of strong ducting in the Eastern Mediterranean in both versions. You've got some patchy ducting down the East Coast, in some cases slightly more than in others. And therefore, you have differences between the models. And you've got one striking difference here over the Baltic in this model that isn't picked up in this one. Now, to see which is right and wrong, you need to be there on the day looking at what happened, and I can't honestly remember. But the point I want to make here with this is that these forecasts are produced from the results of the mathematical weather forecast models, which represent the atmosphere, and in 3 dimensions you can have a look at how the temperature and the moisture varies, and you can do these calculations for the refractive index. And if you do those, you can see if it becomes strong enough to produce a duct to start refracting your signals and cause a tropo lift to take place. Now, because they're not the same models, they will not produce quite the same results. So Pascal uses the Arpège model, which is a Meteor France model, and William uses a CMC GDPS model, all words, but mumbo jumbo. But to a meteorologist, these models are both extremely good models, but they have slight differences in their resolution, in how they're formulated in terms of dealing with moisture in the atmosphere, the spacing of the model calculation grid points and things like that. And all of this stuff means that you shouldn't expect these models to be the same answer. They're going to be similar, but the point to take from this, going back to our slide a moment ago, is that they're giving a heads up position of where things are. It is only a forecast, so when the day unfolds, you'll see that this will be slightly different on the day, but still useful as a guide. So stations in East Anglia here, near where I am in Norwich, you could work up the East Coast to Aberdeen maybe on both these models. On here, you'd expect to have a look across the North Sea and the Channel, and it gives you an idea as to where to focus your attention. So treat those as really useful guides, and it's a bit like knowing knowing where to go fishing in a river. Loads of rivers, loads of places where you could go fishing, but using this to choose where you actually cast in is going to give you a really good heads up. So just to end on our tropo part for the moment, this is kind of a distillation of everything that comes out of looking at this over a lot of years. And the one thing is, on a typical schematic of a weather chart, high pressure is the thing to look for initially. So find your high pressure and you've got a reasonable chance of tropo, but very near the center of the high, be aware that paths that cross that center, the inversion, as I said, when the high develops, the inversion gradually sinks lower and lower and lower. Eventually, it may either reach a hill or the ground on a flat area, and your signal, instead of being ducted for long distances, will get to the center of the high and then it will run out of traction there. So the best way to deal with a high pressure produced lift is to go around the edge of it. So to follow the isobars just on the edge of it, as close to the high as you can, but just on the edge of it without going across. Now, the fact that this high has been around for some time is quite a useful thing, because usually that means the inversion is fairly strong. So that's given it time to build up that real good contrast, and not just a contrast in temperature. It's that lack of vertical motion that a stable layer gives you like that allows moisture to increase underneath the inversion. So the old red sky at night philosophy of tropo was tap your barometer and, oh, nice high coming, we'll have a lift soon, and then wait for the pressure to start to fall, the barometer to start to fall a bit, and then you get your best conditions. And that's usually in this country, in Europe, when the high drifts to the east, you start to draw in moist air underneath the inversion and you get a better contrast, because it turns out that moisture to contrast, that difference between moist foggy air and the clear air above the inversion is the key. If you've got a foggy morning, it's a real good sign. So what else can we say about where to be or not to be? Well, actually, to be close to the low is a good not to be situation, because the isobars here suggest strong winds, so that would break up the turbulence, would break up any inversion, and air in the region of high pressure and fronts is generally rising, not falling. You can get, as I say, air from the southwest increasing moisture. I'm just trying to go back to doing these in order, going down, and then sometimes you'll get a high appearing after a front has gone through. So you get a high and then another low. So quite often in the weather world, you either get highs that are very much blocking features, they stay around for a long while and they're the ones that produce good conditions, or you get them that act as, if you like, placeholders between two lows. So they will move with this pattern and move almost as quickly as the lows, and tend to give you the hint of high pressure and inversion, but not very well developed, and won't be as productive as this one would be. Lastly, that sort of bonus point, the sort of little extra ingredient for the NFD weekend, is if a front goes through overnight or at any point, and the cold front is just clearing away to the southeast, you can sometimes, because of the way the upper atmosphere is organized behind a weather front, you can sometimes get a temporary lift going on immediately parallel to the front just behind it. So anyway, plenty there to get your teeth into for tropo. Right, I think we've exhausted tropo. Now we're going to get on to something which does take quite a bit of time to sort out, and horror of horrors. Now, we're not going to deal with all of this. This is what I've distilled Sporadic E down to in my mind. Now, there's a lot of work going on in professional research areas. It's a very hot topic at the moment, Sporadic E. It's been a hot topic in amateur radio for decades. And there's a lot of work just moving us forward all the time. The fact that this schematic has so many areas of interest on it just shows how complicated the whole deal is. And what I want to do today is to show you some of the things that have developed in the last couple of years or so that I've noticed through looking more closely at some of the elements of it. We're going to have a little look at the Meteors for a moment, but mainly we're going to concentrate on the stuff down here, the bits down here that have a big say in where ease occurs. So sporadic E is formed by the physics of what goes on in the ionosphere in the E region. And the location of sporadic E, that is the interest in why it happens where it does. What makes it crop up in that part of Europe more often than that part? And is there a reason for it? That bit is the bit that fascinates me. And it's because it probably has some fold back on these features here, the weather part, because all of these things are capable of generating turbulence in the atmosphere, sort of wave motions. And sometimes wave motions, like on the surface of an interface between sea and air, like the ocean waves, just propagate along, and they're called gravity waves because gravity is the restoring force, but you can get them in the air as well. And if there's no cloud, you can't see them, but there's wave motion in there and you experience it as turbulence in an aircraft. So atmospheric gravity waves are the link between the weather and the E region. And it appears that these things do have a lot of say in where sporadic E happens. So jet streams are one of the key things. And on upper air charts, the same way as on a surface weather map on the television forecast, you'll see isobars. Here on upper air charts, we call them contours, and they're fixed pressure values. And what you plot is not the pressure value, but the height of that pressure level in the atmosphere. It's just the way it is. But the point is, you can treat them as weather charts in the same way you can on the surface television map. And where the flow is strongest, you'll have jet streams. And they can be quite contorted. It's a bit like a sine wave on an oscilloscope. And sometimes it ripples along nicely, and sometimes it sort of locks and becomes very static. Sometimes it's very low amplitude, and sometimes it's very high amplitude. And all of these things alter how it behaves and how it propagates. One of the other ingredients, and a particularly important one for us in Europe, is the interaction of jet stream flow across mountains. And we're very well blessed with lots of high ground ranges in Europe that are very often affected by jet streams blowing over the top of them. When that happens, you get these most amazing cloud shapes sometimes. If there's moisture in the air flows up over the top of the mountain. The moisture condenses, the flow goes through here, and as it descends down the other side, it evaporates. The cloud is no longer visible, but it remains locked to it. So it's being eroded here and constantly replaced with new cloud here. So it's a fascinating thing, but it's a wave, it's a form of a wave motion above a hillside. So now, keep your nerve, don't worry. This is, I'll take my time going through this bit because it's quite an interesting thing, because one new thing I've been looking at, jet streams, to be honest, I've felt have accounted for at least 80%, probably better than 90% of the locational part of where ease occurs. But sometimes you get jet streams which are very weak, like on this shading here, which this is a type of chart which we use on PropQuest, which you'll be able to see later on if you've not already used it. So here we have very weak jet stream, very pale green color. And the stronger the jet stream, it goes into the yellows and the oranges. And then these other faded sort of colored lines are lines to show where the pattern's changing a lot. So blue represents an increasing value of the contour heights, and red where it's falling a lot and decreasing. So it can either represent development of a feature, which is another reason for making lots of turbulence, or movement, which is also capable of producing turbulence. Anyway, point of this is, on this particular day, the wonderful map from dxmaps.com showed quite a cluster of paths going across the northern North Sea. And in here, there wasn't really a lot going on apart from a couple of weak jet streams. But another way of looking at properties in the atmosphere which can make turbulence is to look at vorticity or relative vorticity, the local vorticity. It's a type of way of describing the spin in the atmosphere. And it's just another way of trying to find out what's really going on in a moving atmosphere and what might be important for generating turbulence. So I've been looking at those during this season, and this picked out a very thin but quite intense line of vorticity across the North Sea in association with this feature here. And it's just ahead of the axis of this upper ridge that's toppling down, and been trying to get a link between relative vorticity and upper ridges and other regions which might produce paths. So sometimes you have to look at more than one source. It's work ongoing, but it's an interesting development, and it's something we can factor into one of the many reasons why we might be getting sporadic E where we're getting it. Thunderstorms, go without saying, are very dramatic things. Huge, intense amounts of energy, strong up currents in a big sort of thunderstorm. These thunderstorms over Turkey, I mean, some of these, the tops of them, punching through this stable layer at the top of the atmosphere, vertical motion in here, 100 miles an hour, you know, tremendously strong vertical updrafts. And that's going to cause a lot of turbulence where it interacts with the stable layer, and you often see evidence of ripples radiating out where it hits the tropopause. But a true test of how things are going is to have a look at a day when there were multiple openings. So on the chart here, I've marked 4 regions where there's sporadic E being reported. So if you look at the midway point, we'll assume that we're dealing with a midway point, or else somewhere where multiple paths crossed in different orientations. So we got one in Germany, one over the northern Atlantic, Norwegian Sea, one just north of the Pyrenees, and another one over Crimea. Well, if you look at the satellite picture on the right-hand image, there's cloud in the northern one, in the Norwegian Sea, North Atlantic, north of the Faroes. Not very obvious what's going on there. A little bit of cloud, barely obvious, showing up over the Pyrenees. No cloud at all showing up over this crossing point over the Crimea. And just the hint of some linear features in the cloud over Germany on this one. Which linear features are good things, by the way, because it represents like a crest in a wave. So it suggests there's something more organized. Anyway, that's something that might make you think, oh, well, that probably is something to do with what's going on here. But when we look at where the jet streams are in this situation, you'll see that the northern one is on the edge of a jet stream. The one in Germany, northern Germany, has got a very marked jet stream core there present. The Pyrenees has got a jet stream blowing down onto that. And we saw earlier on how good the link is between jet streams and mountain ranges for generating these wave motions. And even over the Crimea, the other arm of this jet stream is present too. So it's a fantastic correlation. And in fact, jet streams do account for the largest number of events when you're looking for sporadic E. So if you were to go for anything that's currently available in the public domain to try and predict where you think sporadic E might happen, this isn't about whether it's going to happen or not. It's about where it happens if it happens. Then looking at upper air jet stream maps is as good as you can do, pretty much. So I then followed on with some interesting questions from people who have been following sporadic E during the season this year. And I got a question from a GM station who was very keen on 10-meter activity. And he was working on this left-hand chart down to the Caribbean. And the question was, well, how can you get, you know, how unlikely is it to get these things where we've seen in Europe in the past, that previous chart we looked at, we were looking at single hop. These are all single hop paths. So you've got one reflection point. But what do you have to do when you get multi-hop paths? How likely is it that you'll get that many strong reflecting points all arranged in a line like that? Well, and it was also present on 6 meters too. These dots on DX maps represent the point where it meets the ground. So you have up to the E region, down again, interaction with the surface, up to the E region, down again, interaction with the surface, up to it, and so on. So 3 hops. So the question is, how can that fit in with our ideas of jet streams? Well, this came a bit too late for me to get the actual data on the day, but looking at a reanalysis data set, this is a very good site. It's a NOAA site which reanalyzes data compares it against climatology. So for that particular date, 19th of May this year, it found these anomalies between the background wind field and what actually happened on the date. And you've got hot spots of excess over the average wind speed, in this point where we would have had the first hop, you know, from the E region. We've got a spot here for the second one and another little spot here for the third one. So it is possible to get them aligned. Now, these multi-hop paths on Sporadic E tend to be much, much weaker than the single hop ones, because each point you've got potential for some loss. If the E's reflection is doing its job properly, there shouldn't be much at these points, but there could be quite a bit at the interaction with the surface. But let's say for a point here, this great circle map does kind of look as if it's a neat fit, isn't it, for jet stream affected wind speed produced in the hotspots. So how reasonable is it to expect this? So let's take this looking at averages a bit more closely. And if we then look at the average for the whole of the month of May, this is the month of May on the left-hand image, and the colours represent the average wind speed in that month. And here's the UK on the right-hand side where the cursor's waving around. And you can see that you've got, on average, quite a distribution of stronger winds over the Atlantic and down as far south as the Caribbean region in the month of May. This is a very strong feature, a permanent feature in the transition season, the subtropical jet stream. And that's quite strong here. There's also the polar front jet stream showing up here off the coast of northeastern America. Anyway, point is, compare the May graphic with what happens if you look at the mean for the month of July. Two things jump off the page here. One is you've lost all of that wind strength in the southern half of a route from GM to the Caribbean or anywhere else in Europe. So the typical picture in this high summer is that you don't usually have the stronger winds to produce the second or third hop particularly. You do still have a strong jet stream, if anything, slightly stronger. The focus of attention on the northern polar front jet off the coast of the States is now much greater. So you would, on the face of it, now I've not looked into the logs for this, but some of you out there who do this regularly would doubtless be able to do this and think, now I'll do a check on this, because my assessment from this would be paths to the Caribbean on Sporadic E would tend to favour the early season and would be much less common in the high summer second half of the season, just because of the changes in the mean upper air wind pattern that happens during this time of the year. But yet you would still get, and it's not the same as saying you can't get transatlantic paths, but you would still get paths across to the States via multiple hops along this jet stream. Anyway, interesting thing to go away and do research on. And that's the other nice thing about Sporadic E work, isn't it? That you have the ability to do your own research. This is this ongoing improving the knowledge thing, and amateurs can play a big role in doing this. So for all of you who submit your logs to the various clusters, there are so many good clusters out there. There's no any one that's different or better than the other to the point where you'd say you only go to this one. They're all good. They all add to the knowledge base. But it's how we can look at these things and see how realistic this becomes as an operating guide. Anyway, so remember this, we looked at all these complications and had a little diversion into the bits at the bottom here about the weather. But I just want to spend a brief moment talking to you about the contribution of meteors, because meteors turn out to be, well, they're now widely regarded as the source of the fuel that makes Sporadic E. So when a meteor burns up in the upper atmosphere, the ionization produced lasts a long while compared to the normal ionization in the E region, which is a daytime driven thing. It's called a Chapman layer. So it increases with the elevation of the sun and decreases and so on. And it's all being ionized and recombining, and it follows the sun's path. So meteors don't. Their ionization lasts a lot longer, and it does become quite a good marker for when to expect E's. And I was talking to John Wasnell, G4BAO, and he put me in touch with this wonderful paper, which has got a brilliant graph in it. And it's all about the background meteor count. And obviously that includes meteor showers as well. We tend to assume sporadic E, you just book time off work when there's big meteor showers and lock yourself in the shack for a week. But there's meteor showers all through the year, but there's also meteors coming in. And there's a continuous delivery of meteor debris from space as Earth makes its orbit around the sun. Now, this is okay. Before you all jump up and down and say, look, this is ridiculous, there's only 2 years here, 2011 and 2012. Well, that's what was in the graph and the paper. But the point is, it's amazing what you can do with something like this, just as it stands. So the first thing I want to say is, before we cover it up with a few things and start looking at things, just look at the difference between the blue and the red crosses, how much difference there is from 1 year to the next, the difference between blue and red, and how much difference there is between one day and the next. So here we have a point here, and the next 2 points are, well, it's chalk and cheese. And there's even some that go below this line to well above it. Anyway, the thing is, there's huge variability in the daily meteor count. But anyway, I've said here on the right, no idea what would be a good threshold for this, but just as a thought experiment, let's see what would happen if, say, we set a threshold of 8,000 meteors per day. Now, that would give you a period early in January when meteor count is pretty high, and that takes you up to about the 15th of January. And it would also give you a period for the main season when it peaks here in the center, from about the 3rd week in May, 24th of May, to the 6th of September. Pretty close, but there are others where these individual dots can go above it. The markers can go above that line. So in a freak year, or maybe not, we don't know. It's only 2 years we're looking at here. But it's quite interesting, isn't it? How this line does come close to, I've tinkered around with 7,000 as well. You get slightly broader season. But you get the point. It's possible to see why it is that in our operational experience of sporadic E, it tends to favour these certain periods. And it works for me. And I just want to drop in one final thing here, because I'm conscious of time, and there's a couple of really important things to put in. This green area here, look at these points here that go above the line. Okay, it's a long while ago. But let's just say, although the main curve has gone below, it's not unknown for random events to take it well above. Right, so the next challenge is to combine all of these different things from that big schematic, loads of those ellipses, into one factor. And my colleague Dan Holly and I have done this now in map form. And we plot it on a map, and these radial ring lines, 700 and 1200 kilometers, show roughly a typical distance for the middle hop reflection point. So we're looking for intensity of color here, so good intensity there. So you think beaming, well, there's nobody in the mid-Atlantic, but beaming east, there's a bit more color there. So that's what we've been developing on. And this E's probability index, it's trying to help us gauge some probability of location. So the weather factors come out as a number between 1 and 100, say, and then we adjust it up or down according to what these other factors might look like. Remember all those ellipses up at the top, what the meteor background level is, what the KP index is, things like that, which can all affect the likelihood of E's. But this is all about the whereabouts is E's that I'm looking at here. And I've also added in the vorticity parameter into this multi-factored API. There's a lot of work still to be done, but this is just a way of bringing you up to date to show you where we've got to. So the developments over this coming winter will be to be able to plot your location with a call sign, and plot a distance station that you've just worked with a call sign and locator, plot the Great Circle path, and show radial rings for the half distance, plus or minus, say, 50 kilometers, and see what it looks like. So that's all coming up. The other thing that I was asked about a few times were the paths across the polar regions to JA, and those were happening earlier on in the peak of the season. And you can see on the Great Circle maps, you can see the paths. And it struck me that these actually, in the summer, in the high summer, a lot of these paths will in fact go through areas where in the summer season, lows and their fronts and their jet stream meanderings will go across that part of northern Russia. So it's quite feasible to think maybe this is just a normal form of sporadic E. And let's see how this one works when you look at the different hot points. And this is what we'll be programming up hopefully over the winter to be able to do this, click of a button. And you can see they can locate with increases in the value of this propagation index. So it's not beyond the bounds of possibility that these paths can't be put together as a traditional multi-hop ease path. So it's an area of activity from the G3YLA shack at the moment, trying to get some way of visualizing this smoothly and quickly on the day. So here's an example of a testing. You won't be able to see this on your version of this site, but here's an example of putting in two locator squares, plotting the path and seeing what it looks like in the midpoint. And there you can see a very nice signal on the midpoint there for that one. This was an FT8 QSO. So another thing that we've got to do is to try and imagine what sort of value of threshold we need when we've settled on a value that we think works in general. What value correlates with FT8 and what value you need to be enough to do CW or SSB. Maybe they're similar, maybe they're not. And here's another one, goes across a zone, but it's a broad zone. And one of the interesting things is when you get large jet stream areas, what it is that makes one part of the jet stream more effective at ease than another. So that's something else that will come up during the development work. And then you have a bust. It's like all these things. Once you think you're getting somewhere, you're going well, and then a bust. And this one produced two paths, well, multiple paths. I've just highlighted these two to make the graphic. One going this way, it goes in a null. And this one going east-west goes through a null. So this is a bit of a blow. But when it turns out, you look at things, these are all based on forecast charts. So this probability index, by the way, is all based on a model's forecast of where the fronts and the troughs and the jet stream areas are going to be. And over a period of time, there'll be small errors creep in. So it may not be exactly right. And sporadic E is quite a finite, sort of precise locational thing. So it's maybe not too surprising if it perhaps hasn't got this bit of the jet stream far enough north and these rapidly falling contour heights. Patchy, misty, low cloud, no sign of thunderstorms, or at least nothing that sort of waves flags there. But on the vorticity, there's a very strong maximum in this region, and it's probably that which is causing the path. But the model EPI calculation, we hadn't got enough of priority given to it at that point. So one of the things we'll be looking at is what to do when you've got a strong relative vorticity reading. So it's a way of adjusting the figures. And just when you thought you got all your rules all nicely gathered together, end of the season, hands up all those who don't bother looking much for sporadic E after the end of August. Well, this was the 6th of October, Tuesday of this week. You know, we're not talking about just after the end. We're talking about a long while after the end. And this is the 6-meter plot here on the left. Paths all over the place, and even managed to produce paths on CW. So I ended up working down into Sardinia and into Naples. Very strong jet stream. You can see these orangey colors in the jet stream strength. So that alone would be a good sign. And particularly at this exit region where it intersects with the Alps, very, very good sign. Vorticity showing up. This I've shown. I don't think the vorticity part it per se was as perhaps interesting as the jet stream bit was, but you can see how the vorticity maximum here runs along the edge the northern boundary of the jet stream. So that's something that comes out of some of these things, that maybe that's interesting, but it's definitely paths to the south here across this jet stream overall, which seems to be producing the turbulence. So let's see if we can do anything else with that. Oh, did that go the right way? I don't know whether that did. Oh yes, here we go. So my paths, yes, my paths down to Sardinia and Italy have indeed crossed an area of slightly enhanced EPI index. But the thing that struck me was that it's where it crosses the Alps that's probably more important. And when you look at the cloud cover for this jet stream, can you see these striations over the area of northern Italy and just starting over the Alps? So there's a lot of gravity wave, mountain wave activity going on there. And we are in a meteor shower. There's, as John G4BAO mentioned, 3 of them for this week in last Sunday's GB2RS. So really good when something comes together. Rain scatter, I'm going to have to skip along a bit quickly here. So rain scatter, use that for many of the radars online you can use for finding where the strong reflecting areas are. And then I just want to do a quick thing about the PropQuest website. Loads of good information there during the Sporadic E season, but also for working at other times of the year. This panel, you click on each one and you can get 6 hourly intervals of where the jet streams are. You can plot the FOF2 from 3 different stations, Fairford, Chiltern and Doubs in Belgium, and you can see how that changed. The FOEs is this purple set along the bottom here. E's incidentally shows up as a sharp spike, so it's often a very transient thing. And recently we've just added the NVIS plot of the more significant elements for local nets within a HF scenario or LF bands on 80 meters, where you want skywave NVIS communication. So FOEs, FOF2 and the FXL, all of these, if any of them are above the band you're on, say 80 meters, then the chances are you'll have reasonable chance of getting an NVIS net. If they're all below, then the band will have dropped out. And then the last point here to make is that something else comes out of doing these things. Sometimes you see something that you didn't expect to see. And one is that if you look at the averaging, you can work out averages for months going back. And at the beginning and the end of the season, there tends to be, well, what I can describe as a more uniform peak around midday for the maximum value of FOEs in the month. Compare that to the high season, June, when you have a peak in the mid-morning and then another one late afternoon and early evening. So that's the traditional view we have of Sporadic E. And it's different from the start of the season to the end. So just want to say a big thank you to Dan. It's always difficult grabbing a screen grab, but Dan is the programmer who put a lot of work into doing this website for us. It's a great resource for amateur radio. He's not an amateur, I'm trying to convert him, but he's done a huge amount of work for us. So thank you, Dan, for that. And also thank you to Weathercrest for letting us put the site on your server and providing us with the weather data that we use to plot the charts. So then I go off and do the propagation report for the bulletin, and there it is, and it goes off to the RSGB and you hear all about it on the Sunday. And that, I think, is plenty enough for this morning. Thank you.
Absolutely brilliant, Jim. I don't know if you've been reading the chat, you probably never had the time. Some amazing reaction on the YouTube chat. Many comments, 1 or 2 questions. I'll get to those in a second. But a lot of people saying, thanks for not tidying up in the background, Jim.
It's a proper shack.
These things here are hiding a multitude of sins, I can tell you. Absolutely, absolutely brilliant. Well, look, Tim Kirby, GW4VXC from Practical Wireless and Radio User, says very interested in the transient openings that seem to happen along, and he puts a question mark after along, weather fronts and squall lines. Any comments on that?
Yeah, good. A good pickup there, Tim, because those weather fronts and squall lines are the very things that are good contributors to gravity wave turbulence. So they're good sources of energy for making these waves that propagate all the way up to the E region. So when you're in the east season, then just about any cold front or any squall line will produce a reasonable chance of getting sporadic E somewhere along the line. You have to work so much harder at that when you're outside the main ease season, because various other things are not on your side at that point. And we haven't really explored all of those in today's talk. But yeah, excellent point. Looking at weather maps and seeing when these squalls go. Well, radar would do that as well. Picking up the squall line on a radar display is good too.
He also wonders if climate change is going to have an effect on propagation.
Well, it will. I'm sure it will. For example, just off the top of the hat, top of the head thing, you would say the different number of blocking events when you get static areas of high pressure being locked off in one part of a chart or another, that will affect the frequency of occurrence of tropo. Mobility of weather systems across the Atlantic due to different temperature contrasts between the much warmer poles and the tropical regions, that may be changing, or it may be changing because of increased meltwater, cold water flowing into the northern half of the Atlantic. And that's not even getting up to the ionosphere, where as you change the climate of the lower part of the troposphere where the weather is, what happens is the top bit cools down. So the layers are sort of sinking a bit down there. So all of the recombination rates of the ionization will change. A hugely complex thing, very interactive, but you're bang on the money. These are things which will form, a lot of discussion in the years ahead.
And Olaf, who's joining us after 12 o'clock to talk about HF contesting, he wonders how high up these winds are. Do they make it into the F? Do they make it into the F layer?
Well, there is evidence of gravity waves extending up into the F region, as far as I understand it. I've tended to have a sort of a glass ceiling at the E region, and certainly there's measurements there. There's been some very good images of launches of rockets that have gone up through a clear sky, and you can see them and see the trail. And when you see that, you'll see the vapor trail sort of distorted. And it's a remarkable insight as to how much wind shear there is up there. So there's a lot of work being done on identifying the propagation of these gravity waves going upwards, but also there are gravity waves that propagate from other areas of interest, and the ionosphere would need a different set of experts to play with. I can launch them from the weather bit, but you're right, Olaf. There are lots of similar things that get up as far as the F region.
Okay, we've got to move on very quickly now. I suggest that you do look at the web chat, Jim, when you finish, because there's some glowing reports for you on there, glowing comments. It's been brilliant. Ian, GM4VXM, says he's going to have to run this talk through several times to take it all in, as I think are a few of us. And I know you've written for Radcom before now, but he wonders, have you thought of writing a book? Simon Keeble says more or less the same.
Yeah, well, this business about retiring and finding you way busier than you ever thought you had time to go to work in. I have got a book on the stocks, and the RSGB will be very pleased to hear that I did actually start writing out chapter headings and a few bits and pieces. So it's plan A is to do the book. I've done a few little sketches of what's going to be in the different bits, so it will happen. And sympathies with you who feel that this is a lot to take in. I mean, there's far more been left out than has been put into this. And over a long period of years, from back in the late 80s when I started tinkering with Sporadic E, it's amazing how much things have evolved in that time, and it does need some way of writing it down, or going back and looking at videos again to just pause and take a bit in at a time. It's very complex, which is why I've had to produce the ease probability index, because it just blows my head off to try and get my head around it all at once. It's a very complex thing, but so satisfying. If you can look at something like that, say on PropQuest, and say, I know why the band sounds like this at the moment, whether it's the FOF2 trace changing or whether it's a Sporadic E coming up in that particular place. You can say, yeah, that's why I decided to go fishing there.
Excellent, Jim. I've seen so many of your presentations, and it still hasn't gone in here. The only thing I can remember about the weather is what my friends at the BBC Weather Centre often tell me, is that if we say it's going to rain and it doesn't rain, it doesn't mean it didn't rain, it just never made it to the ground. That's all I know.
Worked for me every time.
Yeah. All right, Jim. Thank you very much. Thanks for sharing and passing on your expertise in this fascinating subject. And hope to see you again at one of the rallies, or Newark, or the convention next year. Keep our fingers crossed.
Yeah, really looking
Thanks
forward.